This module is perhaps the most important module in the whole course. This is the bridge between descriptive and inferential statistics. This is how we go from, a sample to making generalizations about a population. And so we're going to start looking first at how we do this with percentages. And in the next video, we're going to talk about quantitative variables and see how we do the same process with population means. So here's our fundamental problem. We have some categorical variable that has two classes. A lot of times categorical variables do not have two classes, but you're generally interested in just one. So for example, if I'm looking at religion, right, I can have Catholic, Hindu, Lutheran, Jewish, Muslim, blah, 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 right? And the whole point is that I'm going to just look at one. So I may look at Christian, and then everything else becomes not Christian. And so this is what we call a binary categorical variable. It has two values. And I'm going to look particularly at the binary categorical variable, whether or not a person would vote for Trump in 2020. And so we know what our population is. These are all the people that we would need data from to answer that question. And so what we want to know is we want to know the value of the parameter for this categorical variable. Remember what a parameter is for a variable. It's the one number we would want to compute if we could have all the values of that variable from the population. So if I was an omniscient being and I knew every registered voter, their yeses and nos, okay, whether they were going to vote for Trump or not, what would I want to do with all those yeses and nos? What's the one number I would want to compute? Well, I'd want to compute the percentage of the values that were for Trump. And so our parameter, when we have a categorical variable, is a population percentage. And sometimes we use the word proportion for percentage. And of course, what do? We take a random sample. And again, samples estimate populations. So what do? We get an estimate from our sample. And that sample percentage is supposed to be close to the population percentage. It's going to estimate it. Now, before we get into the details of this, we have to talk about one issue, and that is how we're doing the sampling. So if you look at the data, there's roughly 14 million registered voters in Florida. And let's just suppose, this is a hypothetical, that 50% would vote for Trump. Then we know there's 7 million that would vote for Trump, 7 million that would vote for Biden. And of course, this is an oversimplification. There are third parties and all this sort of stuff. But I just want to illustrate a point. So here's my population. Of course, I don't know the political affiliation of these people. This is what I have to figure out. And so let's particularly pick this specific voter and ask, would they vote for Trump? And before we pick them, we know the probability is 50%. Now, let's suppose that they do vote for Trump, okay? So now things have changed a little bit, right? When I pick the second voter and I ask, are you going to vote for Trump? Notice I have one less Trump voter, and I have one less than the whole population. So I don't have 50% exactly, but when I compute that number, it's so close to 50% that we essentially say it's 50%. So this sort of sampling scheme is called sampling without replacement. In other words, it means that when we got our response from the first voter, we didn't put him back in the population, right? We kept them out. And the question is, how long can we get away with doing this, okay? Well, it turns out that if your sample size is less than 10% of the population, you can assume each time you draw an individual from the population, the probability it will fall into one of the categories is the same as it was in the original population before you did any sampling at all. Okay, so this is kind of the idea. The population is so large, it's like catching fish in the ocean, right? You're on a boat in the middle of the ocean. What's the probability you'll catch a tuna? I don't know, whatever, say 10%, right? Now you catch a tuna and you keep him out, you're gonna go eat him. You throw your pole back in, what's the probability that you're gonna catch a tuna? Well, does that one tuna that you took out of this huge ocean of tuna really affect your likelihood? Of course not. This is the same sort of idea. Okay, so I want to do a little bit of experiments. We want to begin to understand what sample percentages look like. Okay, and so what we're going to do is we're going to go ahead and we're going to simulate that poll in the introductory video I talked about from CNN. But we're going to assume, unlike the poll which said it was 48% Biden, 48% Trump, we're going to assume the percentage that would vote for Trump in the population is 50%. And what I want the computer to do is I want the computer to keep on drawing samples, random samples, of 766 people, a whole lot of times, over and over and over again. So it'll draw a first sample, a second sample, third sample, and so on. Now, each time it draws one sample, it puts those individuals back in the population. Okay, while we're doing the sampling, we're doing it without replacement. But when we go to choose another sample, we put the previous sample back in. So we're always sampling from the original population. And let's just suppose we get 20 samples, okay? So these are all random samples of the same size from the same population. And then what we're going to do is we're going to compute the sample percentage for each sample. And our goal is we want to understand the pattern that the estimators form. Remember we said in the previous module, I think it was back in module 3 actually, that the distribution of variables formed patterns. We're going to see that the estimators also form a pattern, and we're going to see why that's important. But for right now, let's just worry about getting it. And so let's just say hypothetically it looked like this. We know that if we're taking random samples, they should be centered around the parameter value, which is 50%. And there we go. So this is the sort of game we want to play. Now, doing this in real life would be incredibly time-consuming and expensive. It takes a lot of effort just to get one good sample, let alone 20 or even more. And notice that even if I got the sample, I still can't tell where the population mean is. I mean, I'm going to take the average of these sample percentages, but it's probably not going to be the population average. So I need something a little better. So what we're going to do is we're going to enlist the computer. And the computer can take random samples ad nauseum. So it can do this for us. And so you're going to go ahead and click on this link right here. And it's going to open up a website. And it's going to open up a website right here. And let's kind of unpack what's going on here. So it looks like there's a lot of stuff on this page, but actually it's pretty easy to understand once you see what's going on. So first, we're doing a simulation, so you have to tell the computer certain values for the input. And what we're doing, notice that it says probability of heads. What we're doing is we're modeling the outcome of each voter by flipping a coin. If the probability that a randomly chosen voter was going to vote for Trump was really 50%, it's the same as the probability that a fair coin flipped is going to be 50%. So I can kind of model it by a coin flip. So I'm going to assume the population percentage is 50%. This is my sample size. It's a number of tosses, right? and I only want one sample. I need to change a few other things. They're not essential, but it's going to help us visualize what's going on. I'm going to go ahead and I'm going to click on proportion of heads. In other words, this is going to give us the percentage of heads. Or in our case, kind of translating it to the voting analogy, it's going to give us the percentage of voters in our sample that vote for Trump. So the default is it's click to number. We want percentage. And finally, I'm going to click on summary statistics. So we're going to see that when we get this pattern of estimators, what are we going to want to do with that data? Well, we're going to want to compute its center and its spread. Okay. And now we're going to run the program. Go ahead and click Draw Samples. And the output's going to be here. Okay, first, the program's going to output the mean and the standard deviation of all of our sample percentages, and it's going to plot them down here. So go ahead and do that. If you're watching with me, you can do it right now. If you're watching at home, go ahead and pause the video and fill in those fields and run the simulation. Okay, what do we see? Well, we see our output here. We've drawn one sample. We found the mean and the standard deviation for all the sample percentages. Well, we only had one, right? So the mean's the value that we have. And there's no standard deviation when you just have a single value. And finally, we see that value plotted on a dot plot. And so you got 503 if you're doing this correctly, right? You probably didn't. And why? Because we're drawing random samples. So it's highly likely that you didn't get 50.3%. You got something different. You might have, but it's not likely. And that's the point. We're almost all going to get different values because the sample percentage itself is a variable. Every time you draw a new sample, you generally get a different value. And so the key thing to realize is that we're actually building up a sample of sample percentages. And this is really odd. And one of the reasons why this concept that we're going to talk about today is so difficult for us to wrap our minds around, because we generally don't work with samples of samples. So if you go back to this picture right here, way back. Oops. We don't generally work with a sample of samples. If we had a bunch of samples, what would we do in real life? We would clump them all together, okay? Now statisticians do. There are certain times, and we're going to talk later on in the second video of when we do this, but in your experience up to this point, you haven't worked with samples of samples. So this is a new concept. Okay, so what we want to do now is we want more samples. Okay, I'm going to keep sampling. I'm going to use this program to continually sample. So I had one sample here. So what we're going to do now is we're going to add 999 more samples. Notice you don't have to change the other fields. They remain the same. So I'm going to get 1,000 samples total. I'm going to go ahead. I'm going to draw them. You click Draw Samples. And you notice now that these are the 1,000 sample percentages that I got from 1,000 samples that I drew randomly on the computer. This is the pattern that the sample percentages are forming. Okay. We see the mean. The mean is around 50%, and we see the standard deviation. Now, it's important to understand that the purpose of a histogram, which comes from sample data, is to estimate the population curve, right? We want to estimate the population distribution. That is that smooth curve that we're kind of drawing through this data. This is the best fit curve that kind of cuts through the data evenly. And I've just sketched something here. Okay, I didn't actually compute this. But you can see this curve looks like it fits pretty well. And the population of all the sample percentages is called the sampling distribution. This is a really important term. So this blue curve, the population that we think we would get is if we took samples over and over a gazillion times and each time computed the sample percentage. This is called the sampling distribution. And it looks like it has a normal distribution, and it does. We're going to find out in a minute, okay? Before we get into the details, though, of what that distribution looks like, there's a few things we have to kind of clear up here. So we're going to see that, in fact, those sample percentages have a normal distribution. This comes from mathematical probability theory, so we know this, unambiguously. But a couple of things we have to think about here. The first is that all of this is only guaranteed if our sample is good. And you remember what a good sample was. It was a sample that was chosen randomly, or if it wasn't chosen randomly, it was at least representative of the population, right? There was no obvious bias going on there. And it was large enough. And so we're going to see now that there are actually specific conditions that define what large enough means. And when we can start to use sample percentages to say something about the population percentage. A little bit of notation, and this is important. The thing you want to realize is that the variable and the estimator are different things here. Our variable is a categorical variable, and its population parameter is the population percentage pi. What we get is the sample percentage, which we denote by small p. So these are important points about notation. The population percentage is represented by the symbol pi for small p, right? That's the Greek letter for small p. So p percentage. The sample percentage is just written with a regular p. Okay, what about the estimator? Okay, first of all, we have to realize we have two different distributions going on here. We have a population distribution and we have the sample data distribution. So when I want to talk about the population mean of the sample percentages, remember, percentages are quantitative. Our variable's categorical, but the summary statistic, the estimator, is going to be quantitative. So it has a mean. So the mean we always represent by the Greek letter for small m, and this is pronounced mu. And this is the mean of the sample percentages, which we recall as small p. And the standard deviation of the sample percentages, well, we always use the Greek letter for lowercase s, sigma. And to make it very clear that we're talking about the standard deviation of the sample percentages, we use a p here as a subscript. Now, what about our sample mean and our sample standard deviation? So for sample means, we use x bar rather than mu. And for sample standard deviations, we use regular s instead of the Greek letter for s. Now we're ready for our main result. And this is perhaps the most important fact in all of statistics. If you're going to really understand one thing in this class, it would be this slide. And this is called the central limit theorem. And it's called the central limit theorem because it literally sits at the center or the heart of statistics. If we did not have this fact, we could really not do any meaningful statistics. The statistics we could do would be very, very limited. So first I'm going to state the central limit theorem on this left-hand panel, and then we're going to compare what's predicted from the theory with what we saw from our simulation. So first of all, our sample has to be good. It has to be random, or at least representative of the population, and it needs to be large enough. And there are two conditions, and we have to meet them both for the sample to be large enough. The sample size n times the population percentage has to be greater than or equal to 10. And the sample size times 1 minus the population percentage, this is the probability that you're in the other category, also has to be greater than or equal to 10. In other words, you have to have 10 individuals in both categories in the population. That's what that means. Okay, we always have to check these conditions first whenever we want to use the central limit theorem. And if we pass those conditions, then we automatically know what the pattern for the sample percentages look like. We can say they have a normal distribution. And you know from your work in the last section that whenever you have a normal distribution, you need to specify two things to uniquely identify that specific distribution. The first is the mean, which happens to be the population parameter pi. And that's not surprising, because we said before that if we're taking random samples, our estimates should be scattered around the actual parameter value. And our standard deviation is given by the following formula. Pi times 1 minus pi divided by the sample size, and we take the square root of all of that. So we can put it together using our compact notation, and we can say the following. The sample percentages have a normal distribution with mean pi and standard deviation of the square root of pi times 1 minus pi over n. Okay, what about the simulation we did with this applet? Well, first of all, was our sample random? Yes, because the computer chose it. And computers are much better at human beings when it comes to choosing random samples. Was it large enough? Well, we had a sample size of 766, and the percentage in the population that were going to vote for Trump was 50%. So we get 383, which is greater than or equal to 10. And if we check the other condition, sure enough, we find it's also greater than or equal to 10. So now we can use the central limit theorem. So it tells us that our sample percentages should have a normal distribution. And the theory says I'm going to go ahead and put in my population percentage, which is 50%. So my population mean is 50%. And my standard deviation, I put in my population percentage and my sample size. It's going to be 0.018. So this is sigma sub p, and I'm sorry, this is mu sub p, and this is sigma sub p. Now, if we compare that with what we got from our sample, this is back on slide 7, our x bar sub p, 0.501, really close. And our S sub p, the standard deviation, the sample standard deviation of the proportions is 0.018, and out to the third decimal place, they're the same. So you can see that what we got from our sample was really close to the theory. but the theory is exact, whereas the simulation is approximate. And of course, we don't know if we're exactly on or not, right? And we usually won't be. So let's go to our first reading quiz question. So you might remember that in the introductory video, we looked at that poll from CNN, and it said that 48% of the voters were going to vote for Trump in that sample. And so let's suppose that the population percentage that are going to vote for Trump is really 48% in Florida. And suppose this week, the Trump campaign takes a random sample of 1,000 Florida voters. Can we use the central limit theorem to find the distribution of the sample percentages? So in other words, I want to check these conditions, okay? We can always assume that polls carried out, or I shouldn't say we can always, but we do assume that polls carried out by polling companies are random, okay? Or at least they're representative. Sometimes we're wrong. I mean, the exit polls in the 2016 presidential election were wrong, but we generally make that assumption, okay? So this is going to be true. We're going to assume this is true. And we really have to check and see if the sample is large enough, okay? And so if you've convinced yourself that both of those conditions are satisfied, and this is our pi here, our 48%, right? And our 1,000 is our sample size. We're going to use that information to check our conditions here that we required to satisfy. If you're convinced that they're satisfied, what distribution of sample percentages should they see? In other words, what does the central limit theorem tell us about the population, about the sample percentages that I should see? Okay. So go ahead, take a minute and answer that. Okay. I want to talk a little bit more about the center and the spread of the sampling distribution for the sample percentages. An important thing to know is that the sample percentage is an unbiased estimator of the population percentage. Okay, what does that mean? What that means is that if you look at the sample percentages from random samples, they're centered around the population parameter value. And I want to go back and talk about this bullseye analogy we looked at before, right? So these would be estimators from a random sample. Again, remember, we're trying to hit the bullseye, the parameter here. And if we take random samples, they're going to be centered around the bullseye. Okay? So we say here that our estimator is unbiased. The center of the estimates is the same as the center of the population parameter. Okay? Same thing. On the other hand, if we don't sample randomly, or our sample is not representative of the population, we're going to be oversampling one group more than the other. That's going to throw off our values. And then we say our estimator is biased. In other words, because we're oversampling a particular group, right? Our values are going to be centered around a different value. So suppose, for example, when the Trump team took their estimates, they oversampled the panhandle, which is primarily conservative, right? What that means is that their values are going to move off center. And so they're not going to be centered around the population parameter. And actually, this difference between where the sample estimates are centered around and where they should be centered around the parameter, that's called the bias. That's the offset in those two centers. And if we look at this, say in the picture that we're going to be working with, okay, we're not working with bullseyes, we're working with, plots on number lines, okay? This top plot would be unbiased. In other words, if this blue line is the population parameter, the estimates are centered around the population parameter. Okay. And again, if we took it from a biased sample, they're going to be centered around a different value here. Okay, good. So that takes care of the center. What about the spread? And this is the really interesting part. Okay. We all know that larger sample sizes are better. I mean, that's kind of something that everyone's known since grade school. The question is why? Well, we have in our mind this intuitive notion that as the sample size gets larger, the estimates become more precise. They become more tightly clustered around the parameter value, and they can't go as far away. So again, kind of going back to the bullseye analogy, okay? If we have estimators from large samples, the estimates are precise. In other words, they're very close to the actual parameter value, which is what we want an estimate to be, right? Think about like a car estimate. On the other hand, if we have estimates from small samples, without putting too fine a point on it, we don't have the ability to average out the extreme values as well. And so they tend to be more scattered. They have a greater spread around the parameter value. And again, these are both random samples, right? And so low spread means low standard deviation, right? Standard deviation is a measure of the spread. High spread, high standard deviation. And what the central limit theorem does is something really cool. It not only, it not only kind of gives us this qualitative picture, but it actually tells us exactly how the standard deviation changes. It tells us that this is the formula for the standard deviation. And we can understand how the sample size comes into play. The standard deviation goes like 1 over the square root of n. And so if we look at this picture, okay, these are sample percentages from the same population using random samples of different sample sizes. So we can see that when we take samples of size 25, using this formula, the standard deviation looks like this. We're dividing by 5. That's how the sample size is coming in, the square root of 25. And we can see that it's broader. On the other hand, if we take a sample size of 100 and plug it into here, the square root of 100 is going to be 10. And so we're dividing the same number by a larger number here for the larger sample size, and therefore the standard deviation is going to be half what it is here. And you can see this. The distribution of sample percentages becomes more and more clustered, tightly clustered around the actual value. And since these are normal distributions, we know we can't get more than 3 standard deviations away. It's very unlikely, okay? So what happens is that 3 standard deviation window, that range that contains 99.7% of the data values, gets smaller and smaller. In other words, the range of allowed data values gets smaller and smaller as n gets larger and larger. Okay, let's go ahead and piggyback off of what we learned in the first reading quiz and get a little bit more into the central limit theorem. So same problem as before, okay? The Trump campaign team takes a random sample of 1,000 Florida voters where the population percentage is 48%. We found out in the last reading quiz that yes, you can in fact use the central limit theorem. And now what I want to know is how likely is it that they'll get a sample percentage of 50%? So let's assume the same thing, that the population's really 48%. The Trump campaign takes a random sample of 1,000 voters. And let's suppose they take the sample, and this time they don't get 50%, they get 44%. Now, remember this criterion that we used way back in the beginning of statistically significant. We said if there was less than a 5% chance of something occurring, it was statistically significant. So what we want to do here is we're working with the same population. So I want to take this population right here. And for this population, for this normal distribution, I want to compute the percentile of 44%. And I want to find out if it's less than 5%. Okay, good. So take a minute and do that. Same calculation, except now you're doing the lower tail. For question 2, you did the upper tail, right? For values above the mean, you use the upper percentile. So here you'll be using the lower percentile, which is generally the default. So go ahead and take a minute and do that. Okay, so to recap here, when we have a binary categorical variable and the percentage of the population in one of the categories is pi, and we're repeatedly drawing random samples of the same size from this population, we want to know, what does the population of the estimators look like? This is called the sampling distribution. In other words, it's the distribution that we get from the samples. I love statistics because things sound like what they are. Sampling distribution, right? Distribution of what you get from samples. And what we saw today was that the sample percentages have their own distribution. And the central limit theorem tells us precisely what it is. It says that if we meet these 3 conditions, then the sample percentages have a normal distribution, the mean is pi, and the standard deviation is the square root of pi times 1 minus pi divided by n. Okay, so now you're going to go and do the homeworks. Now, when you're doing the homeworks, how are you going to recognize when to use these techniques? Well, you're going to be looking at sample percentages. And you're going to be basically asked the question, how likely it is I got a certain sample percentage if I assumed the population had this percentage. This is a sort of format that you're going to be following. A good idea as you start to work problems in the future, and this will help you a great deal, is to learn to begin to kind of take a problem apart. Remember I said previously that statistics is not mathematics, but they're word problems, right? So what we want to do is we want to be able to dissect the word problems. When you're working a problem and you're totally lost, and this happens to me too, by the way, okay, some things are really, the way people word problems and whatever can be really, we're kind of weird. We want to do a couple of things. First of all, we want to figure out what the parameter is. And we're going to tell, we can tell that by the language. We're either going to be given a mean or a population percentage. Okay, a mean or a percentage. So if you see, I'm sorry, yeah, a mean or a percentage. I'm going to leave out population because it's understood. Okay. If you see percentage, you're working with, a categorical variable, right? A mean quantitative. From there, you want to figure out the variable. Okay, mean of what? Or percentage of what? Okay. It's always good to know what variable you're working with. Then you want to know your population. You kind of work backwards almost. Okay. Now, once you have those 3 pieces of information, then you want to figure out the sample information, right? Now you want the sample data, the sample information. So you always want the sample size. And you want the value of the estimator. Once you have that, you've kind of flowed the problem. You have a good idea of what's going on, and you can actually work on the problem. If you don't know these 5 pieces of information, at least the parameter, the value, the sample size, and the estimator, you can't do the problem. So when you're confused, kind of dissect the problem like this, and you can't go wrong. Money back guarantee. All right, thanks for watching. In the next video, we're going to find out that just a central limit theorem for population means also. And I should say sample means also. And we're going to talk about that. Thank you.